Today we're going to look at our last three gas laws. The first one being Dalton's Law of partial pressures. Dalton's Law of partial pressures simply means that when you have a container that has more than one gas in it, the individual pressures is equal to the total pressure of all of those gases. So for example, in this picture, we have oxygen gas on the far left that has a pressure of 159. And then we also have nitrogen gas in the middle at a pressure of 593. So when those two gases are put into the same container, they would have a total pressure of 752 because oxygen plus nitrogen's pressure gives you 752. So it's a sum addition, the sum of the partial pressures that equal the total pressure. And that formula right here is given to you on page 3 of your reference table. So anytime a problem has a ton of pressures together, it simply means that it's a Dalton's Law problem. So we're going to look at two examples. Really important that you label what you're given and what you're looking for so that you can understand what type of problem this is. So the first thing that we come across is 731 torr. And if you read it, that tells you that that is the total pressure. So we're going to label that PT, T for total. Then we come across 15.5 millimeters of mercury. And the problem tells us that that is the pressure of water. So we're going to label that pH2O, pressure of water. That's everything that was given. So now we're looking at what we're looking for. And that's the pressure of oxygen. So the unknown that we have is PO2, or the pressure of oxygen. Notice that we have more than two pressures. Anytime you have more than two pressures, it's considered a Dalton's Law problem. Now, one of the issues that we have here is that the pressures are two different units. It doesn't matter what unit it is in, we just have to be in the same unit. So here's a little bit of review for how to convert pressure. You take your given, 17.55 millimeters of mercury. We're going to convert that to torr so it matches our total pressure. So we bring millimeters of mercury down to the bottom and we put torr on the top. Then we look on page 1 of our reference table and we notice that 760 goes with millimeters of mercury and 760 also goes with torr. Millimeters of mercury would cancel, leaving us with 17.5 torr. So here you can see that torr and millimeters of mercury are interchangeable. So really, did we have to do that math? No, I could have just changed millimeters of mercury to torr because I know that they're the same. Now we can look at Dalton's Law. The total pressure is equal to the sum of the partial pressures. So in this case, the total pressure is equal to the pressure of water plus the pressure of oxygen. Now the formula given to you on page 3 has P3 plus ... That means you can have 2 pressures, 3 pressures, you could have 15 pressures added together. It doesn't matter how many gases you have added together. In this problem, we only have 2. So we're going to plug in what we know. The total pressure is 731. Pressure of water is 17.5, and we're looking for the pressure of oxygen. This is the only time we are not multiplying and dividing. This is the only time we're going to actually subtract. So we subtract 17.5 from both sides. That gets x to be by itself, and we have an answer of 713.5 torr. When you add and subtract, the significant figures are based on the fewest decimal places. And since our total pressure and our partial pressure of water both had 1 decimal place, our partial pressure of oxygen should also have 1 decimal place. But that's the end of the problem. Let's look at one more. Hopefully you find these to be the easiest type of gas law problem. So here in this problem, we are told that there are 5 gases. The first gas has a pressure of 5 atm, so we're going to label that P1. The second gas has a pressure of 2 atm, so we're going to label that P2. Then it says the rest have a pressure of 1.5. So we don't know what P3 is, P4, and P5. We just know that P3 through 5, all of those together, have a pressure of 1.5. We're looking for the total pressure, so we're going to solve for PT this time. All of the gas, or all of the pressures given to us, are all in ATM, so we don't have to worry about converting this time. So the total pressure is equal to the pressure of P1 plus P2 plus 3 through 5. So notice this time, these two formulas look very similar because we don't know the gases, we're just numbering them. Plug in the numbers. We're solving for the total. So again, we're going to add these together. This is the only time we add and subtract. And we get 8.5 ATM. Now, because when you add and subtract, it's based on, significant figures are based on decimal places, and 5 ATM and 2 ATM have 0 decimal places. We want 0 decimal places in our answer, so we're going to round that up to 9 ATM. Next, we have Avogadro's law. Yes, it's the same Avogadro as Avogadro's number. He found that the volume and the amount of moles of a gas are directly related. In other words, the more volume you have, the more moles of gas you have. The less moles of gas you have, the less the volume is. So if we were to graph this, it would show a direct relationship, which remember is that straight line. We're going to look at 2 examples. So here we have argon gas. We have 3.25 moles, so that's our N1, at a volume of 100 liters, so that's our V1. And then it says that it's at a temperature and pressure, and then it's asking us for a different situation, but at the same conditions. That's telling us that we're using Avogadro's law because temperature and pressure are being held constant. So we have 14.15 moles, that's our N2, and we're looking for volume, so that's our V2. 2 volumes, 2 moles, that must mean it's Avogadro's number, or Avogadro's law. Now we're solving for V2. V2 is on the top, but we need it to be by itself. So we're going to multiply both sides by N2. Then we can plug in the numbers. 14.15 times 100 divided by 325. Moles will cancel, leaving us with liters. And so we have an answer of 435 liters. Let's look at one more problem for Avogadro's law. Here we have 5 grams of oxygen gas. Can't do anything in grams, so we need to convert that to moles first. So we take our 5 grams, bring grams to the bottom, mole on the top. Remember, oxygen's a diatomic, so we're going to add the mass twice. So instead of 16, we're using 32. And that's the amount of grams per 1 mole of gas. Multiply and divide, grams will cancel, leaving us with moles. So now that we have moles, we can label this N1. Next, we have 7.20 liters. That's a volume, so that's V1. Then we have 15 grams. Again, can't do anything with grams, so we're going to convert that to moles. Grams gets tossed to the bottom, mole is on top. Molar mass is still 32 because we have 2 oxygen atoms for every 1 mole. Multiply and divide, grams cancel, leaving us with 0.469 moles of oxygen. So that's going to be my N2, and I'm looking for V2. So again, if we're looking for V2, it's already on the top. We just need to be by itself. So we're going to multiply both sides by N2. Then we can plug our numbers in. N2 times V1 divided by N1 equals V2. Moles will cancel, leaving us with the volume, and we get 21.6 liters. Now, some of you might have realized, did we really need to convert it to mole? No, because we would be dividing by the same molar mass, we really didn't have to be in mole. We could have done that in grams. I just wanted to practice converting grams to moles for you. Finally, we have effusion and diffusion, and this will lead us into Graham's law. Effusion is when the gas passes through a small opening, like when your tire gets punctured with a nail and all the gas escapes through that small opening. That's effusion. And that picture is shown down here at the bottom. Diffusion is when two gases mix together. So diffusion means to mix, and that's what's shown in this upper portion. Diffusion is why when you walk into the perfume section of a department store, it can smell really bad because all of those different gases are mixing together. So what is Graham's law? Graham's law simply says that heavy particles will move slower than lighter particles. Or in other words, lighter particles move faster than heavier particles. So it's all based on the molar mass. So if I am given a list of gases and asked which one is faster or slower, I need to look at the molar masses. So that's what we're going to do first, is determine the molar mass of all of these substances. So CO2, carbon and 2 oxygens, have a molar mass of 44. CH4, carbon and 4 hydrogens, is 16. Xenon is an element, so we just need to copy that one from the periodic table, 131. And then 2 hydrogen atoms would have a mass of 2. So which one would move the fastest? That would be the one that's the lightest, which is hydrogen. And the slowest would be the one that's the heaviest, which is xenon. So some of the problems are that simple, where all you're doing is you're comparing the molar masses. Sometimes a question can ask for the rate, how much faster? And that's where we calculate Graham's law. So Graham's law is the rate. Sometimes you might see it as R1 over R2. Sometimes you might see it simply as rate. So the rate is equal to the square root of the heavier molar mass divided by the lighter molar mass. Remember, the lighter it is, the faster it moves, so that one has to go on the bottom. So when we're looking at our example here, what is the rate of HCl compared to NH3? We have to know which one is the fastest and which one's the slowest. We have to know the molar masses. So for HCl, we're going to add hydrogen and chlorine, and we get 36.5. NH3, nitrogen and 3 hydrogens, we add together and get about 17. So to find the rate, we're using the square root of their molar masses. The heavier one goes on top. So HCl is going to go on the top, and then ammonia on the bottom because it's lighter. So right away, I know that ammonia should be moving faster than HCl. This square root of their molar masses is going to tell me how much faster. So when we divide and then take the square root, we get 1.5. So we could say ammonia moves 1.5 times faster than HCl, or we could say HCl moves 1.5 times slower than NH3. That ends all of our gas laws. If you have questions, please reach out through Remind, email, or Microsoft Teams. Have a good day.